Rogue planets are celestial objects that are smaller than brown dwarfs, which are themselves intermediate in size between planets and stars. Astronomers typically distinguish between planets and brown dwarfs based on the ability to burn deuterium. This occurs in objects that exceed roughly 13 times the mass of Jupiter or 0.013 times the mass of the Sun. The first rogue planets were discovered in 2000 and were relatively massive, exceeding 5 times the mass of Jupiter. These objects were detected using optical and infrared observations in star-forming regions, suggesting they formed similarly to stars through the collapse and fragmentation of a molecular cloud. Smaller rogue planets, particularly those much smaller than Jupiter, are challenging to detect directly with optical and infrared telescopes. However, they can be identified using gravitational microlensing. This phenomenon occurs when a massive object, such as a rogue planet, passes in front of a more distant star, bending and magnifying its light. Through this method, astronomers have detected rogue planets as small as 0.3 to 2 times the mass of Earth. Estimates based on microlensing surveys suggest that rogue planets are extremely common in the galaxy. There could be around 2 trillion of them, with Earth-sized ones being far more abundant than larger Jupiter-sized ones. In fact, rogue planets may outnumber those orbiting stars by a factor of 6. Since they drift freely through space without a host star, most rogue planets are thought to be cold and inhospitable. However, some theories suggest that if a rogue planet retains a thick hydrogen-helium atmosphere and generates internal heat from radioactive decay, it could have liquid water on its surface, creating conditions favorable for life. Additionally, moons orbiting rogue planets might be more suitable for life, especially if they have thick atmospheres that trap heat or experience tidal heating, which could warm both the moon and its parent planet. Detecting extrasolar planets, including rogue planets, is a challenging task because planets are much dimmer than the stars they orbit. The most effective technique for finding exoplanets has been the radial velocity method, which measures how a star moves in response to the gravitational pull of an orbiting planet. This technique led to the first confirmed exoplanet discovery in 1995, when Swiss astronomers Michel Mayor and Didier Queloz identified 51 Pegasi b. Radial velocity observations help determine the mass and orbital characteristics of exoplanets. Astronomers also use gravitational lensing to detect planets, whether they orbit stars or drift freely through space. By closely monitoring distant stars, they can identify when a planet or another massive body moves in front of them, briefly magnifying their light. The larger the intervening object, the stronger the lensing effect. This technique has been instrumental in uncovering both exoplanets in star systems and rogue planets wandering alone in space. As technology advances, astronomers are rapidly improving their ability to detect smaller and more distant planets, while also learning more about previously discovered ones. Most known exoplanetary systems differ greatly from our own solar system, but this may be due to current technological limitations. Many planets similar to those in our solar system might still be undetectable with existing methods. Since many surveyed stars appear to lack detectable planets, scientists are still uncertain whether our solar system is typical or an anomaly in the universe.